In this lesson, we will learn to interpret graph of motion in stationary, moving with constant speed, and accelerating states. We start our lesson. Let's review some common characteristics of graph. A Cartesian coordinate system typically consists of two axes, x and y. The y coordinates of the graph represent the dependent variable, while the x coordinates are the independent variable. In all of the scenario we'll discuss here, the x-axis will be time t, and the y-axis will be position of x of t, velocity v of t, or acceleration a of t, respectively, in our three separate graphs. bt, at. The graphical representation of a function is commonly referred to as a curve, even in cases where the curve is a straight line. Recall that the point where the curve meets the y-axis is called the y-intercept. The rate of change of the function is graphically represented by the slope and can be discerned using any 2 points on the curve. In some cases, the area under the curve can also provide useful information. The area under the curve can be found by calculating the geometric area of the shape defined by the graph of the function. Now that we have reviewed these characteristics, we can begin our study of time graph. We'll begin by examining a stationary object first. On a position time graph, the position of an object can be determined at any given time, t, simply by referencing our vertical axis x of t. In a Cartesian coordinate system, the x and y coordinate of a point are given by x and y. In this case, the x value is time and the y value is the position at the time. Note that the object is not moving, therefore the position value is constant and is graphically represented by horizontal line. The slope of the curve on the position time graph gives us the change in position per change in time. That fits our definition of average velocity. Since the slope of the position time curve is 0, we note that the average velocity is also 0. Our velocity time graph is therefore a flat line emanating from the origin. Like the lead line. The value of the velocity at any given time can also be determined from the coordinate of the velocity time graph. In this case, we see that the velocity is constantly 0. Next, recall that acceleration is defined as a equals delta v over delta t, which is actually the slope of the curve on the velocity time graph. Accelerations. Since the velocity of a stationary object is constantly 0, the slope is 0, resulting in another flat line emanating from the origin. in green line in this graph. The graph of a stationary object may seem pretty dull, but notice how the information in each graph had a relationship with another graph, each other. We'll see this trend continue as we examine the remaining cases of motion. Let's examine the characteristic of the third time graph in the case of an object moving at a constant speed. We'll begin with the position time graph. As in the stationary case, we can determine the position of the object at any given time and any time t by the coordinates of the function at this time. The curve in this case is a straight line with positive slope. The slope of the line represents the change in position per time, which is the average velocity. Note that the slope could be negative, and that would represent an object changing its position in the direction defined as negative. In this example, the function that defines the curve is x of t equals vt plus x initial. Note that this is a form y equals mx plus b. That means the y-intercept of the line corresponds to our initial position on the position time graph. You might also notice that the slope of this line is v. We can now use the wealth of knowledge gleaned from our position time graph to create our velocity time graph. The curve on our position time graph was a straight line with a constant slope. That means that our average velocity over the given time interval is constant. Constant velocity corresponds to a flat line of some value on our velocity time graph. The slope of the function on our velocity time graph is 0. Slope is 0. The area under the curve on our velocity time graph corresponds to the change in position. Change in position. Note that since our curve is a flat line, the area under the curve forms a rectangle. The formula for the area of a rectangle is length times width. In this case, the length is velocity and the width is time. Or delta x equals vt. Our equation for a change in position with constant velocity. Or delta x equals vt, our equation for a change in position with constant velocity. Now, let's construct our acceleration time graph for this scenario. Acceleration is change in velocity per change in time, or the slope of the curve on our velocity time graph. Well, the slope was 0, therefore our acceleration is also 0. Once again, we have a flat line emanating from the origin over the given time interval. Once again, we have a flat line emanating from the origin over the given time interval. The graph of an object moving at constant speed were more interesting than those of the stationary object. We'll see that as an object's motion increases, the graphical information grows proportionally.